Welcome to the deep dive.
Good to be here.
So let's talk about something potentially game-changing today. Imagine vaccines, important medicines that maybe don't need that constant deep freeze.
Right. Stuff that can reach pretty much anyone, anywhere, much more easily.
Exactly. And we're diving into a U.S. patent today that, it seems to point in that direction.
Yeah, it's patent number US 12,263,217B2, just granted this past April 2025.
And the title is Nucleic Acid Stabilizing Solution for Vaccines, Therapeutics, Storage, and Transport. It's from a company called Dakin Molecular Systems.
Quite a title, but the core idea is what we want to unpack.
Right. So our mission for you, the listener, is to get a quick handle on what this patent is really about. The key innovation.
And why it matters, especially for things like mRNA vaccines and therapies everyone's been hearing about, without getting totally swamped by the technical jargon.
Perfect. Think of it as the fast track. Our main source is the patent itself, the claims, descriptions, figures, the whole thing.
And the central question we're digging into is, how does the solution actually work to solve the stability problem for these delicate nucleic acids?
What's in it? And, crucially, what's the evidence? Does it actually work?
Okay, so let's start with the problem they're trying to solve.
Yeah, why is this needed?
Well, as the patent lays out, nucleic acids, especially RNA, are just inherently unstable molecules. They tend to break down.
Degrade. Right. They're fragile. I think you used the analogy of a delicate flower before.
Something like that, yeah. They just don't hold up well on their own, especially outside very specific, often cold conditions.
And this isn't just a small thing, is it? This fragility, it's been a real hurdle for some advanced medicines.
Oh, absolutely. Particularly for mRNA technologies. We all saw the headlines, the huge logistical challenges around keeping certain COVID vaccines at those ultra-low temperatures.
It's deep freeze requirements, yeah.
Yeah.
Made distribution really complex.
Exactly. And the patent points this out. Current methods often rely on that deep freezing or something called lyophilization.
Lyophilization, that's like freeze drying, right?
Essentially, yes. And while these methods work, they are often costly and logistically they're just really complex, especially for getting treatments out globally.
To places without that kind of infrastructure.
Precisely. So there's a clear need for alternatives.
Okay, so this patent proposes a different approach. Not necessarily the extreme cold. What's their solution?
It centers on a liquid solution, a kind of stabilizing cocktail, if you will.
The cocktail, okay.
Yeah, designed to basically create a protective environment for the nucleic acids, keep them intact for longer and over a wider temperature range.
A protective bubble, kind of. So what's in this cocktail? What are the key ingredients?
The patent highlights three main components. First, there's a chelating agent, specifically EDTA.
EDTA, okay. Ethylenedium and nitrous acetic acid. I think I've heard of that.
You probably have. It's quite common. They suggest a concentration range, typically around 0.026 molar up to 1.0 molar.
And what does the EDTA do?
It's crucial. It grabs onto metal ions. These little metal ions can act like tiny scissors, basically, speeding up RNA degradation. EDTA binds them up, takes them out of commission.
So it's like a bodyguard, neutralizing these RNA-damaging ions. Makes sense. What's number two?
Number two is a buffering agent. They specify TRICE.
TRICE. Triethydroxymethylaminomethanes.
That's the one. Commonly used buffer. Its job is to keep the pH stable, super important for nucleic acid integrity.
Why is pH so critical?
Well, if the pH swings too much, it can promote chemical reactions that break down the RNA. TRIAS keeps it in a happy zone, typically between pH 7 and 9, according to the patent.
So neutral to slightly alkaline.
Okay.
TRIAS is the environment controller. And the third ingredient?
The third one is a salt. Specifically, sodium chloride and ACl, just regular table salt.
Salt, what does that do?
It's used to adjust what's called the ionic strength of the solution. Think of it as managing the overall electrical environment. This affects how the nucleic acid molecule folds up, its structure, and ultimately its stability. They suggest concentrations from about 0.15 molar up to 3.0 molar.
So EDTA grabs the metals, TRS controls the pH, NaCl handles the ionic environment. Sounds like a really thought-through combination.
It seems synergistic, yeah. Each part playing a specific role.
And what are they claiming this solution can achieve? How much stability are we talking about?
This is where it gets really interesting. The patent claims protection against degradation for anywhere from 1 day up to 180 days.
180 days, that's like almost 6 months.
It is. And importantly, across a temperature range from minus 20 degrees Celsius, so frozen all the way up to plus 38 degrees Celsius.
Plus 38 C. That's warm, close to body temperature.
Exactly. That upper range is particularly significant. It suggests potential for storage without refrigeration, or at least not ultra-cold refrigeration.
That is a massive potential improvement. Okay, the patent also has figures, some visual data. What do those tell us?
Right, figures 1A through 1D and figure 2, which sort of summarizes them. They use these 3D plots.
3D plots, how do those work here?
Think of them like maps. Each axis represents the concentration, the molarity of one of the key ingredients, EDTA, TRS, and NaCl.
Okay, so like coordinates in a 3D space define a specific recipe.
Precisely. And the points plotted on these graphs likely represent the different formulations they actually tested. The clusters or shaded areas show the combinations that worked best for stabilization.
So they're mapping out the sweet spot for the concentrations.
Yeah, figure 1A, for instance, seems to highlight a preferred zone within that 3D space where the solution is particularly effective. It visualizes the optimal recipe range.
That's helpful. But visuals are one thing. Did they include actual experimental data to back this up?
Oh, yes. Figures 3 through 10, and also tables 1 and 2. They present results from experiments testing the solution.
What kind of experiments?
They used, in some cases, actual genomic RNA from the SARS-CoV-2 virus.
The COVID virus RNA. So real-world relevant material.
Exactly. They put this RNA into different formulations of their stabilizing solution and stored it under various conditions, room temp, a warm 38 degrees C incubator, and a native 25 degrees C freezer for comparison.
Okay, and how did they measure if the RNA was staying stable or breaking down?
They use a technique called RT-PCR, reverse transcription polymerase chain reaction.
PCR. Okay. That detects genetic material.
Right. And they report something called the cycle threshold value, or CT value. In simple terms, a lower CT value means there's more intact RNA present. If the RNA degrades, the CT value goes up because it takes more cycles to detect it.
Got it. Low CT, cool, good, stable RNA.
Yep.
High CT was bad, degraded RNA. So what did the results show?
We'll take figure 3, for example. It shows results at room temperature, about 25 degrees C. Certain formulations, which they label pool 1, 2, and 3.
Do they say what's in those pools?
Yes, the figure captions actually give the specific molarities. Pool 1, for instance, was 0.1 MEDTA, 0.075 APRIS, and 0.5 meter NaCl.
Okay, and how did those pools perform?
They maintained much lower CT values, meaning better stability over 40 days compared to RNA stored in just plain water. The difference was pretty significant.
Wow, stable at room temp for over a month. That's impressive.
It is. And then Table 2 gives quantitative data after 10 days at room temp, showing the actual calculated copies of the viral RNA per milliliter. It really reinforces the finding.
So multiple lines of evidence showing their specific combinations of EDTA, TRS, and NaCl work.
Correct. It seems to effectively preserve the nucleic acid integrity, even under fairly challenging conditions like room temperature storage for extended periods.
Which really backs up the potential impact we were talking about.
Absolutely. If this translates to real-world applications, it could fundamentally change how we handle these kinds of medicine.
So thinking about those applications, the patent title mentions vaccines and therapeutics specifically.
Yes, they explicitly call those out. It's highly relevant for mRNA vaccines, obviously, but also potentially for other DNA or RNA-based therapies being developed for various diseases.
And easier storage could make those therapies more viable.
Potentially, yes. Especially therapies that might need to be shipped or stored outside major medical centers. It lowers the logistical barrier.
And the biggest implication seems to be reducing that reliance on the cold chain.
That's probably the headline benefit, yes. Less need for ultra-cold freezers, dry ice, complex monitoring. It all points towards easier, cheaper, and wider distribution.
Which means better global access.
Exactly. Getting these advanced medicines to low-resource settings becomes much more feasible. Imagine the impact on global health equity.
It's huge. Does the patent suggest other uses besides vaccines and therapies?
It does mention applicability for diagnostic nucleic acids as well. Think about storing samples for testing or reagents used in diagnostic kits.
Right, so lab work and diagnostics could also benefit. Seems quite versatile.
And they also suggest that you could tweak the formulations, adjust the concentrations within their claimed ranges to optimize it for different types of nucleic acids or specific storage needs.
So it's adaptable. Now, we've talked about what it is and what it does.
Mm-hmm.
Does the patent give clues about how it works? The mechanism?
It doesn't spell out the molecular mechanism in exhaustive detail, at least not in the parts we focused on, but we can definitely infer how the components likely work together. It's probably a synergistic effect.
Okay, so walk us through that thinking.
Well, first, the EDTA, as we said, acts as a chelator. It binds up those divalent metal ions like magnesium, which can catalyze RNA cleavage. So step one is disabling a key degradation pathway.
Right, neutralizing the scissors.
Then you have the Tri-X buffer. RNA is susceptible to hydrolysis, basically breakdown by water, and this is very pH dependent. Tri-S keeps the pH in that optimal range around 7 to 9, slowing down that hydrolysis.
Keeping the chemical environment stable, and the salt, NaCl.
The NaCl controls the ionic strength. This influences how the RNA molecule folds and interacts with itself and the solvent. The right ionic environment can help the RNA maintain a more stable structure, making it less prone to degradation.
So it's the combination removing catalysts, controlling pH, and providing a supportive ionic environment that likely gives the overall stabilizing effect.
That seems to be the most logical explanation based on the components.
Okay, so let's quickly recap this deep dive for everyone listening. We looked at this Dakin Molecular Systems patent for a nucleic acid stabilizing solution.
Right, a solution using EDTA, TRS, and NaCl in specific concentration ranges.
And the big claim is that this solution can keep things like mRNA stable for potentially months, even at temperatures ranging from frozen all the way up to around 38 degrees near body temp.
The data presented using PCR on viral RNA seems to support this claim, showing significantly better stability compared to just water, especially at room temperature.
And why should you, the listener, care about this? Well, it's about accessibility.
Exactly. This kind of technology could potentially slash the need for those difficult, expensive cold chains for vaccines and therapeutics,
Making it easier and cheaper to get life-saving medicines distributed globally, reaching far more people.
It could really help level the playing field for access to advanced medical treatments.
It truly could. Which leads to our final thought for you to ponder.
As these powerful nucleic acid technologies keep advancing, are these kinds of stabilization solutions the missing piece, the key to unlocking their full potential for everyone, everywhere?
And what other innovations might be just around the corner to help us store, transport, and deliver these molecules even more effectively? Something to think about.
Definitely. Lots to watch in this space.
Thanks for joining us on the Deep Dive.